So yeah, thanks a lot for giving me the opportunity to present my my research. So my name is Alexander Streltsov, and I will talk about our recent results in my group that concern catalytic transformations of pure entangled states. So before we discuss quantum catalysis, let us remind ourselves well, about catalysis in chemistry. That is like the original definition of catalysis. As we know, catalysis in chemistry is the process for increasing the rate of a chemical reaction. So you and the catalyst, a chemical catalyst, is a substance that remains unchanged in the procedure. So an entanglement catalysis is conceptually very similar. So this is a process which achieves entangled state transformations which are not possible without the catalyst. And a quantum catalyst, similar to a chemical catalyst, a quantum catalyst remains unchanged in the procedure. So let us now look a bit more into the details. So let's imagine that we have two parties, Alice and Bob, and they share some quantum state psi. And they want to convert it into another quantum state phi because, for example, because this other quantum state phi is more useful for some quantum network task. Pick your favorite quantum network task where you want to use phi and you want to convert it from psi. So basically, the goal is to convert psi into phi. And the question that you can ask is, when can Alice and Bob convert psi into phi? And specifically, they would like to convert it without using additional entanglement. So they just apply local measurements and they can exchange classical signals for that. And the solution to this problem has been known already for more than 20 years. The conversion from psi to phi is possible if and only if the Schmidt coefficients of the states, if they fulfill a certain relation that is known as majorization relation. So if that sum of the Schmidt coefficients of psi is smaller or equal than the sum of the Schmidt coefficients of phi for all case between 1 and d, then a conversion is possible, and this is an if and only if relation. So let's now pick two states, psi and phi, where a conversion is not possible. And for example, we can achieve that by just picking by adjusting the Schmidt coefficients in a certain way, right? So that this condition is fulfilled. Yeah. Then Alice and Bob will not be able to perform local measurements and classical communication in order to convert psi into phi. But as we know, sometimes catalytic transitions are possible. So namely, we can take another entangled system, attach it to the state psi, and then Alice will be able to perform some measurements, Bob will be able to perform some measurements, and they, by exchanging their measurement outcomes, so they will be able to convert it into phi tensor the catalyst. So mathematically, we have here the initial state is psi tensor the catalyst state, and the final state is phi tensor the catalyst state. So the catalyst has remained unchanged, and this transition now is possible, although it was not possible without the catalyst. So this phenomenon exists, and we knew about it already since 20 years. So the question that I would like to present an answer to you now is, when is catalytic transformation between two states possible? So this question was open until quite recently, and we have solved it in this article, essentially. The solution is that psi can be converted into phi by using a catalyst if and only if the entropy of Alice's subsystem of psi is bigger or equal than the entropy of Alice's subsystem of phi. And this S here is the von Neumann entropy. So it's the Shannon entropy of the eigenvalues of the density matrix, if you want. So minus the sum of lambda I log lambda I, where lambda are the eigenvalues of rho. So this result has a lot of applications. It can be applied to all singlet-based quantum information protocols. So from this result, we immediately know that psi can be converted into a singlet whenever the entropy of Alice's subsystem of psi is bigger than 1. Why? Because remember that psi can be converted into phi whenever the local entropy of the initial state is bigger than the final state. The local entropy of a singlet is 1. So we can convert any state into a singlet when its local entropy is bigger than 1. So this immediately means that we can do teleportation with any state that has local entropy bigger than 1 just by catalytically convert it into a singlet. And as we all know, singlet is useful for quantum teleportation. Singlet is also useful for quantum key distribution or quantum cryptography, if you want. By the same reasoning, any state with local entropy bigger than 1 is useful for quantum cryptography. And we can also use the methods to, we can also apply the methods to noisy, to mixed quantum states. And sometimes we can evaluate when the states are convertible into a singlet, but I will not go into more details on that. But these results are also applicable to quantum networks. So to situations where we not only have Alice and Bob, but we have more than 2 nodes, more than 2 parties. So here I show you, for example, 3 parties, Alice, Bob, and Charlie, and they attach a catalyst here, a catalytic system, and they want to convert their network state into another network state under the condition that the catalyst remains unchanged. So in general, we can also investigate networks with many nodes, n+1 nodes here, and we can derive a condition of that sort. So that a state psi can be converted into another n+1 node state phi when this condition is fulfilled. So the minimum here runs over X, which are systems of all the Bobs. So here, for technical reasons, we have 1 Alice and n Bobs, and X here is a minimization of all subsets of the Bobs. Here we have the entropy of A and this subset, and here we sum over all the Bobs that are not in this set X. And if this condition is fulfilled, then a transition from psi to phi is possible. So this is only, this is not the full characterization of the transition. So we don't know, we don't understand the full set of conditions when transformations between multipartite systems are possible. In the bipartite case, if we had only Alice and Bob, then we can characterize the transitions perfectly. Let me give you a few details on the methods that we have used to prove this result. So we have used approximate transformations. So that means that our final state is not exactly the state phi that we want, but is approximately close to it. And the trace distance between them can be made arbitrarily small. So in the limit of large n, the trace distance between the state that we achieve and the state that we want is going to 0. And tau n here is a sequence of catalysts. So one requirement that we make that is very essential is that the catalyst remains unchanged. That means if we perform an LOCC protocol on the system and the catalyst, and if we discard the system, then the catalyst is exactly unchanged. So this is a very crucial requirement, because if you allow even a slightly change in the catalyst in that process, then you would get something that is called an embezzling. So you can embezzle entanglement in a certain way. So our process induces correlations between, or creates correlations between the system and the catalyst, but in the limit of large n, these correlations go away. So the system decouples from the catalyst and becomes very close to phi tensor tau. So phi is the state that we want in the end. And we also use very recent results on quantum thermodynamics, where such catalytic methods have been investigated very recently. We also use methods from entanglement theory, entanglement quantification, that were developed by Andreas Winter and Matthias Christander quite some time ago. And we use something that is called squashed entanglement, to be more specific. Okay, I think how much time do we still have? Yeah, I wanted to be on time to allow for questions also. Okay, maybe I'm a little bit ahead of time. Okay, let me summarize. we have seen that catalysis provides advantage for entangled state transformations. We have, I have told you that catalytic transformations from a state psi into a state phi, which are both bipartites, of psi and phi are bipartite states, and psi can be converted into phi by using a catalyst if and only if the entropy, the local entropy of the initial state is bigger or equal than the local entropy of the final state. So here I always spoke about the entropy of Alice, but it doesn't matter. In fact, if you have a pure state, you can also use the local entropy of Bob. It's the same. So the von Neumann entropy is the same. This gives a new interpretation for the von Neumann entropy. Why? Well, because this directly tells you that a state with a larger local entropy is more useful than a state with a smaller local von Neumann entropy, because the state with a larger entropy can be converted into the other state by using a catalyst. Well, our results are also applicable to mixed states and to quantum information processing protocols like quantum state merging. So we have also investigated catalytic quantum state merging and catalytic assisted entanglement distillation. For more details, you can read this article called Catalytic Transformations of Pure Entangled States. Yeah, and yeah, well, I'm looking forward to your question. Thank you.
So yeah, maybe to keep things brief, I will also focus on the one question which puts somehow our focus on what can happen in 10 years. What's your impression? What can quantum technology contribute to the success of 6G networks?
Oh, well, okay. So I think maybe to make a link to my results, I don't think that this sort of results will be applicable in 6G networks or in 7G networks or in 11G networks, let's say, because we really require the ability to process a large number of qubits simultaneously in a certain way. Well, with 6G networks, well, my very simple answer: quantum cryptography, right? So that looks to me like the most natural application for quantum at the moment.
Thanks.
Thank you.
Yeah, these slots are rather short, so maybe we move on directly to the next speaker, and we save questions for the panel discussion, though.